3 weeks left. So including this test tomorrow evening. I hope you remember about that. Tomorrow at 6 p.m. I want to meet with you over in the EX building to write a term test, which is on chapters 5 and 6 and 7 and 8. So all this stuff about rotational, banked curves and all that stuff. Remember that? And I think chapter 6 we got into impulse momentum. Chapter 8 chapter 7 I guess we got into work and energy, and now we're all into torque and first rotation chapter here. So hope you had fun. Hope you got it outdoors. I got it outdoors a bit. Just enjoyed the very last of the warm weather, which I think now is gone. It seems like it this morning. This was on Disney Plus. We watched Beauty and the Beast, and so actually, if you've ever seen the movie, it looks like this guy's in a terrible situation and a beast is holding him by the neck and everything, but he really had it coming, if you know Gaston. But if you think of the beast as being the system here, you can imagine all the forces that are acting on the beast. And so one of the things that comes up quite a lot in these static equilibrium problems at chapter 8 is that once you define the system, if, for example, the beast is exerting an upward force on Gaston's neck, then Gaston is exerting a downward force on the beast, which is one of the forces which can provide a torque on the beast. So this would equal the mass of Gaston times gravity acting down, sort of by Newton's third law. So that happens a lot in these problems as if there's a support there, like a mass or something that's being held up, the mass that's being supported pulls downward with a force equal to its the gravity force on it. Okay, so let's review what we're doing with these static equilibrium problems. In equilibrium, an object has no net force and no net torque. So you draw an extended force diagram that shows where each force acts on the object. You set up your x and y axes as before, because you also have to have the sum of the forces in the x and the y direction also equaling 0, or else the whole thing will accelerate around, right? So it has to not rotate and not move. So the way you set up your x and y axes and where you put your rotation axis, none of that matters, really. You can put it in various ways and still get the right answer. You can call x, y, or y, x, doesn't matter. You can put your rotation axis wherever you like, doesn't matter. You do it to simplify your calculations and to solve for the forces that you've been asked for. And just sum them all up, they all equal 0. And the equation that most often comes up is this one, that the sum of the torques is 0, with most of the chapter 8 problems that you're given. But so that's the one I would start with. But if you realize that there's a way to solve it just using the force equations, or if you also need the force equations, don't forget them, I think, is an important skill. So let's talk about this bicep thing. When you hold a ball in your hand, sort of like that, when the beast was holding Gaston, the muscles tense up, and you're supporting that mass. So it's actually the normal force of the ball acting down on your arm, but it's equal to the gravity on the ball. Conversely, when you push down your hand on the desk, your tricep muscles tense and pull your arm backwards. So there's sort of a clockwise torque that can be exerted on this forearm with your triceps, and a counterclockwise torque that can be exerted on your forearm from your biceps. And the equations of equilibrium allow you to estimate these muscle tension forces. Okay. So example, you hold a 6-kilogram lead ball in your hand with your arm bent as shown. The ball is 35 centimeters from the elbow joint, so you define a rotation axis at the elbow joint. The biceps attach to the forearm 5 centimeters from the elbow joint. The forearm has a mass of 1.2 kilograms, so it also just the gravity in your arm has to be supported by the biceps as well. And the center of mass is 16 centimeters from the elbow joint. What is A, the force of the biceps from the forearm, and B, the force of the upper arm on the elbow joint? So we can so this is, I guess, rotation axis. And they've told you that this distance is the 5 centimeters, and that this distance for the M arm or something times G, this distance is the 16 centimeters. And another distance that's important is this one, which is 35 centimeters. So there's 3 forces. This is the mass of the ball, G, acting down. Then there's the mass of the arm. This is supposed to be a little a there, I guess. Times G acting down. And then you've got an upward force from the bicep acting there. And there's other forces on the elbow joint, the rotation axis, which don't exert a torque. But the basic idea is that we're going to do the sum of the torques equals 0. So if you wanted to do all the 4 steps, the sketch and translate is exactly what I just did, except these are now converted into SI units. Meters can be a little better. This 12 newtons is actually just 1.2 times 9.8. It's that mass of the forearm. Okay. You include the axis of rotation. Okay, which we didn't really do, but let's put it right here. Axis. Okay. Next step is simplify and diagram. So now we've redrawn the object as just being a rectangle with all the forces acting on it at the places they're acting. So this is the force we're trying to find of the biceps and the forearm. There's the force of the earth on the forearm. The gravity force is 12 newtons. The gravity force of the ball. And then some force of the upper arm and the forearm, which we don't know, but we don't care about. And whenever I don't care about a particular force, I like to put the rotation axis there, because then the torque is 0 on it. It doesn't come into the torque equation. So represent mathematically is just that simple equation. Torques equals 0. Solve the equations for the quantity of interest, look at the results, check whether the magnitudes are reasonable, et cetera, limiting cases. So let's just do it. What I'm going to do is define the system as the forearm. And I'm going to start by sort of simplifying, like diagramming it. So I've got this force of the upper arm, which I don't care about. This is the axis. And then I've got this one, the force that I'm trying to find, which I'll call bicep. And this one, which is the mass of I call it the mass of the forearm now, times G, easier. And this one, the mass of the ball, times G. And we've got, I'm going to define plus y and plus x, just in case we need those. I would just note that the forces in the x direction are 0, all 0. Fu must be up or down, because all the other forces don't have an x component. So that's important. The sum of the forces in the y direction is just going to be the 2 upward forces. Actually, I guess the 1 upward force is just the force of the bicep. And then maybe, I guess I'll just put minus Fu minus F forearm times G minus M of the beam or the ball times G. But what's more important here is let's do the torques. Sum of the torques equals the torque from U. This one equals 0. plus 0.05 times FB, because this distance here is 0.05, minus, so then that's a counterclockwise torque, so I'll put it as plus. These are both clockwise torques, so I'll put them as minuses. 0.16 times the mass of the forearm times G, minus 0.35 times the mass of the ball times G. And this is what will give you the answer. So you do 0.05 force you want equals 0.16 times the mass of the forearm times G plus 0.35. So when you solve it out, you have 0.16 times 1.2 times 9.8 plus 0.35 times 6 kilograms times 9.8, and then divide it by the 0.05. So I've got A is that F, B is 450 newtons. And then if you were asked for B, what is the force of the upper arm on the elbow joint, that's where you use this equation from up here. You just balance the forces in the y direction. So you'd say that Fu is equal to 450, which we now have, minus the 9.8 times the 1.5 plus the 6. I've got that it's 380, and it is down. So what I did is I guessed the direction by drawing it down on the extended force diagram, and then when I calculated it, I got a positive number, so that meant that my guess was correct. If I just drawn Fu to be up, then I would have got negative 380, and I would know it was a downward force. Okay. I think I forgot about Ed discussion reader today, didn't I? I'm totally out of it here. Did anyone volunteer to be the Ed discussion reader? If you want to raise your hand. There was somebody, but I'd have to look it up on Quirkus. We're going to have to, maybe they're too shy. Sorry about that. You'll just have to shout if you have a question. Yes? Yes? Yes. Yeah, that's a good question. So yeah, the test is on all of Chapter 8, including the stuff that we're learning today. Yeah, that's a good question. Yes? Yep. No, that's F of the upper arm. So there's the net forces, there's 4 forces on it. There's a force at the rotation axis at the joint. That's what we're calculating. And then there's another force of the bicep. So do you see what we're doing here? We're calculating F of upper arm on the forearm. I do care about it. Not the net force. Does that make sense? The net force is 0. Okay. Let's do a couple of learning catalytics questions on this. And again, the point here is that the net force is 0, and that the torques about any axis you want are 0. So here you have a construction worker of mass worker, MW, sitting on a beam. The beam is uniform, so it has, at I guess the 3-meter point, a downward gravity force acting on it of mb times g. It's supported at the wall by some, maybe, I don't know if it's a static friction force, but some force that's parallel to the wall, and a normal force from the wall. So we split that into 2 components usually. I'm going to call it F1 and lowercase n. And it is also supported by a tension from a diagonal cable at the very end. So there's 1, 2, 3, 4, 5 forces acting on the beam. And they all cancel both components, and all the torques will cancel about whatever rotation axis you want. So do you see an equation there that might give you lowercase n relative to some of the other things. So let me give you a minute to think about that. Maybe chat with your neighbor. Okay. Does anybody have an answer? Any of these equations look good to you? Maybe 5 seconds to click in a guess for the 80%. 3, 2, 1, and stop. Oh. Not liking it. So let's just stay on this laptop. It's the answer was 72% of you voted for E, T cos 30. So what I did is I didn't even use torques. What I said, the normal force N, we know that's an X force, and a lot of these forces don't have an X component. So if we think about this equation, equals 0, then I would just have F1 doesn't have an X component. You've got N. These don't have an X component. And then looking at T, we just have to draw our little triangle. If this is T, then this will be like a negative Tx. Here's your theta. And this will be a positive T sub y. So I think that Tx is equal to negative T cos theta. So minus T cos theta. If you solve that out, you get that N is equal to plus T times cosine theta. So I think that's E. What about F1? Can you do something similar? And find, I think it's the same list of equations. It's probably not E, but give me an equation for F1. Check your neighbor. Yeah, thanks, Raphael, for that. So the final exam, which is on December 15th, is certainly cumulative, covering the entire course, chapters 1 through 11. It's a 3-hour final exam. Okay, 5 seconds to click into this question. 3, 2, 1. I'm having trouble with my HDMI, but I can tell you that 93% of you answered C. So, and I think that, let's just check it here. I think what we're doing here is just, let's just balance the y forces, right? So it's going to be F1 minus mb times g minus mw times g equals 0. No, wrong, sorry. There's another force. There's that positive plus tx, right? So that's t sine of theta. So just solving that all out, F1 equals mb times g plus mw times g minus t times sine 30. Okay, so that, and you can pull out the factor of g, and it does look like c. So good. I want to try to solve it for the tension in the cable. Let's do it. So, sketch and translate. I'm going to draw this out. Let's draw a rectangle. Let's define the axis to be the left end. Let's call it a hinge, I guess. So, axis. We've got M1 uniform beam, M1 times G acting down, and we've got the workman, we're calling him now M2. M2 times G acting there at some distance D from the hinge. And this distance is just L over 2 because it's a uniform beam. And question A is asking what is tension T? That's some theta. And question B is asking, what is it? Fx, the component, so if this is a force F, the x component of this force. And I'm going to define y is up and x is to the right. And the system is the beam. So I think what I want to do is what I want to say here. If this is the axis of rotation, and this is the tension acting up like this at some angle theta, then what you, I've drawn this badly. I'm trying to find the lever arm of the tension force. So remember, if the tension acts like this, what you do, the trick is to draw a force line through it, and then the perpendicular distance from the force line to the rotation axis is equal to the lever arm. Maybe I'll call it x or something from here to here. So if this is a right angle, and this is your theta, and this down here is the length of the whole bar, then the lever arm for tension, x is going to be, well, I'm going to say that sine of theta is equal to x divided by the whole length. So x is going to be L times sine theta. So when I do the sum of the torques is equal to 0, then I've got a positive torque from the tension. So it's T times L sine theta. And then minus these perpendicular forces, you just say M2 times G times D, and then that's clockwise, and minus M1 times G times L over 2. So I can just solve that out. I got T times L sine theta is equal to M2 times G times D plus M1 times G times L over 2. So T is equal to M2 times G times D 1 times G times L over 2, all divided by L sine theta. And then for part B, we just say that the sum of the forces in the x direction is equal to 0, and that's just Fx minus T cos theta. So I'd say just Fx equals T cos theta. And we already found tension. So that's how I would do that one. So that's an example of finding lever arm. So quickly want to do a little bit about equilibrium of tipping objects and stability. And then we have another example coming up and another learning catalytics, but feel free to shout out questions. I'm not sure exactly what's going on, but the HDMI for laptop. I don't know why. When I press this, it goes to. Okay. So, you've probably observed if you're on the subway, okay, it's easier to balance if you kind of spread your legs and have an equilibrium which is a little bigger. By assuming this stance in the direction that the train might accelerate, either speed up or slow down, you increase what's called the area of the support, the area between the area of contact between an object and the surface that's holding you up. So that the idea is that if you tilt a little bit, some angle or something, this person A, whose feet are close together, will have now a gravitational torque whose force line is outside the area of support. And then what happens is that this foot right here on the left becomes the axis of rotation, and he starts to tilt over. Whereas if the gravitational torque is above the area of support, then it doesn't matter which side you choose, the rotation axis, you still get a torque which is supported by the other side, so it doesn't rotate you. So the location of the center of mass, or the center of gravity, which is, by the way, the same as, equals to the center of mass, is important for stability. If we draw a line straight down from the center of gravity and it falls inside the base of the object, then we say it's in stable equilibrium. A little shove and the gravity will try to restore it. Yes, question? I see a few questions on Ed. You are. I define you to be Ed Reader today. So the first question says, why is the force from the wall on an angle? I think it's talking about the question involved in B. Why is the force from the wall on an angle? That's a really good question. Yeah, why is it on an angle? Going back, I don't know what happened there. Yeah, so the force on the hinge is as needed. So it's as needed to keep it in equilibrium. So I can see that there's some downward forces and some upward forces. So maybe there is a vertical component, although that's not clear. But it certainly is clear there has to be a horizontal component, because the only other force that has a horizontal component is tension. And so you have to balance that out. But I don't know if it would be up diagonal or down diagonal, but it would definitely have to have a rightward component. But it's just as needed to balance. Do you have another question, Raphael?
Yes, I do, and I have a microphone now.
And you got to turn it on, though.
Hello?
No? I can never figure out all these buttons. Luckily, Pius is here. Volume. Awesome.
Hi. So now it looks like I have a question from the textbook about similar triangles and wheels that is long.
So let's skip that one.
Okay.
Yeah, I know that one with the wheels. Yeah, we'll deal with that later.
And I have the same question again, so that's all I have.
Keep an eye on it though. Thanks very much.
Okay, no problem.
All right. Where the heck are we? I wanted to do an equilibrium. Actually, let's do. While we're at it here, a quick little demo.
New question. Sorry.
No problem.
It's about hinges again. It says, why can't the tension for part A be equal to F over cos theta instead? I don't know. That's what the question says.
Not quite sure. This is for the beam question?
I think so.
Again, just working it out it's one of these things where the equation is pretty simple. It's the sum of all the forces equals 0, or the sum of all the torques equals 0. And you're either using components or you're using torques. This is the bottle thing. So what you can do, so the center of mass of this bottle is somewhere. You can set it up on this in a fancy way. It's one of these party tricks. So the whole thing sort of balances like that. So the center of mass of the bottle is directly over the area of support, which is this tiny little region right down there. And so if I push it a little to the left, whoop, it wants to rotate to the right. The gravitational torque of the entire system for small perturbations tends to bring it back to equilibrium. So that's sort of what is meant by base of support, is that if it's tilted a little bit and the rotation axis becomes now that one side, then which way does the gravity, does the torque from the gravity rotate the object? And if the center of mass is, a line drawn down from the center of mass is within the area of support, then the gravity torque, no matter which way you tip it, is a restoring torque, which tends to bring it back upright. So that's my demo. Thanks. That's always a nice one. All right. So an equilibrium is stable if a slight disturbance from equilibrium results in forces and or torques that tend to restore the equilibrium. And so that would be this, for example, this cone right here. It's a cone on its base, big base of support, center of mass is in the middle. You tip it to the right, gravity will torque it to the left again. You tip it to the left, gravity will torque it to the right again. However, if the base of the support is tiny and you've got, it might be stable in this situation, but if you tilt it a bit to the left, then gravity will provide a torque which keeps it going to the left and it'll accelerate it away from its equilibrium. If you tilt it a bit to the right, gravity will have a torque to the right and cause it to accelerate away from that equilibrium as well. Let's do a quick learning catalytics. You have the center of gravity. So these trucks are loaded in some crazy way with a whole lot of massive stuff so that you don't know what's in there, but you do know the center of mass is at the red X. That's what you're being told. So assuming that these three trucks, A, B, and C, all have their center of mass at the red X, which one of them will tip over? Or none of them will tip over, or do you think all three will tip over? Maybe chat with your neighbor. Pair up, as usual, if you have a friend. You two guys in the balcony, you can yell at each other.
I have a few questions on Ed while we're doing the learning catalytics. First of all, it's a question about static equilibrium, asking if the net torque and the net force are both 0, but the object is still moving, so at constant velocity, is the thing still in static equilibrium?
That's a good question. Yeah, we usually assume that the velocity is also 0 because it's static.
And then there's another good question that I also like. They're asking if they need to know unit conversions for units that are not Canadian units. I'm assuming they mean not SI. So like miles or horsepower.
Yeah, that's a really good question. So, yeah, if there's any numbers, uh, like the number of meters to a mile or something like that, that you would need, I will provide that in the possibly helpful information on the
Perfect.
page 1 of the test. So you don't need those kinds of numbers on your aid sheet. It's again a really good question.
I have a question from me now.
Sure.
Speaking of possibly helpful information, will the value of G and the mass and radius of the Earth also be there?
If needed, yes.
That would be nice. Thank you.
Yeah. Any numbers like that that I think you might need, I'll try to put. And if you don't have them, you could always raise your hand and ask an invigilator as well.
Okay.
But they should be there on page 1.
Perfect. Thank you.
Great questions. Okay, let's do 5 seconds. Click into this one. I think like something's going to tip is my guess. But going once, going twice. Let's see if it works. Oh, it's on aux plate. Nice. Oh, right. So where is it? Oh, I see. It's ah. Doesn't work. Okay. Again, my HDMI is not working. So I think 76% of you answered A, and that was the one that I liked as well. So the idea is for all of these, you draw a line down from the center of mass with your mind or something like that. And clearly for C, it's within the base of support, and so C is stable. B is a little more controversial, but I think, at least the way I drew it, it seems okay. But A will definitely tip. The gravitational torque, which will reach out and pull down from the X, will cause the whole thing to rotate counterclockwise around the left wheel there. So I like A. Okay. I don't think we're going to do that. So that won't be on the test. We're running out of time. I'll just talk a bit about metastability. You can have, here we have potential energy of maybe an atom in a molecule versus x, the distance between it and another atom or something. You can have a metastable state where it could be stable for small perturbations, but unstable for larger perturbations, and then it'll rush away. So you could be in a little local equilibrium. Also, bowling pins do that. They're in a local equilibrium, so for small perturbations, they will rock back and forth and fall back to equilibrium. But if you give a little bit of a larger perturbation, it falls into another well. High energy isomers are long-lived as they are prevented from rearranging their preferred ground state by small barriers in potential energy. Okay. Question.
Me question, not Ed
Yes,
question. Sorry. Would that demonstration also be metastable? Because if you
Yes.
gave it a big push, it would fall over?
Yeah, exactly. That's just like the bowling pins, isn't it? A tiny little push on the thing restores it, but a bigger push makes it fall. It doesn't take much, actually. I'd say that's more of almost an unstable situation. Even a tiny little push tends to tip it. Okay, I do have one more example I want to do, but let me talk a little bit about term test 2. It's the easy thing to remember is that it's exactly like term test 1, except now it's different chapters. Okay, but 10 multiple choice questions worth 2 points each, and then 1 written question worth 8 points. And this exact same room you wrote it in last time, over in the EX building, and just show up there tomorrow night. And that's all you need is something to write with. You need your calculator. You need your T card. Don't forget some photo ID. That's important because we're going to be collecting your signatures again and looking at your face. You're allowed a paper English translation dictionary. If English is not your first language, that could be helpful. The invigilator may kind of flip through there and just make sure there's not extra stuff. And of course your aid sheet, don't forget. And things that I want you to write in your aid sheet are the equations that you don't want to memorize. Okay? Which I don't find there's tons of in these chapters, but you can put anything you want in there, examples or something. During the test, you have to get your phone away from you. Okay. Remember, there's a double-sided answer sheet. So on one side you bubble, on the other side you write your written answer question. Don't forget to do that. We're going to be kind of strict about that. Not allowed a smartwatch, that kind of thing. These are the rules from last time, so I'm whipping through them a little fast. But let's do an example soon. Because people have been asking me about this mastering physics question on static equilibrium. Have some time? Yeah, I do. So let's do this a little carefully. The figure shows a model of a crane that may be mounted on a truck. A uniform rigid horizontal bar of mass M1 is 100 kilograms and length 5.6. Now you may have got different numbers on your mastering, MyLab and mastering, just because these are sometimes random. But you've got string A pulling up a distance 2 meters from the left end of the bar, is connected to the top plate, and string B is attached to the left end of the bar and is connected to the floor and is pulling down. Make sense? And somehow that keeps the whole thing from rotating in any direction. There's a mass out here, it's 3,000 kilograms, a distance of 5.4 meters. Okay. And the question is, it's on the very bottom, find TB, the magnitude of the tension in string B. So, what I'm going to do, my trick here is, well, first of all, define the system is the horizontal bar. And since I need TB, the tension of string B, then what I'm going to do, my little trick here is and I don't care about TA, I'm going to set the rotation axis to be at the force I don't care about. And then I'm going to use torques to solve this out. Don't care about TA. Whoop. TA. So let's define axis of rotation. This is a little shortcut at that point, at point A. So I'm going to draw, you might draw your axis over on the left since all the forces are acting from there, and that would work. That would be okay. But then you'd have a torque from string A and you'd have no torque from string B, and so your torque equation wouldn't really work for string B, and there's a lot of Y forces here. So I think it's a lot faster to do it my way. So then what will happen is, if we diagram this thing out, here's the thingy. Let's draw in red all the forces. I've got, trying to get red. I've got TB acting down there. I've got TA acting there. I've got halfway point. I've got M1 times G acting down. And at this point, I've got M2 times G acting down. And so this is the distance. D is 2 meters from there to there. And that's from again, the rotation axis is here. This distance, I think, is going to be L over 2 minus D. Since this is L over 2, and we've got D as this left portion. You were told in the problem that this is X, so the distance we need here is actually X minus D. Okay. And what I want to do is sum up all the torques to be equal to 0. Find the tension. So I think I've got 0 is equal to TB times D. Now that is a counterclockwise torque around this axis, right? So that's plus. And then I've got M1 times G times L over 2 minus D. That is a clockwise torque around the axis as I've defined it, so that's a minus. And then I've got M2, I got another minus from M2G times X minus D. So these lever arms are from the rotation axis that I have chosen. And I just simply solve for TB. T is M1 times G times L over 2 minus D plus M2 times G times X minus D. I think we have numbers for all these things now. D is 2 meters. L over 2 minus D is, I think, 0.8 meters. And X minus D is 3.4 meters from the data we were given. So TB is just equal to 100 times 9.8 times 0.8 plus 3,000 times 9.8 times 3.4. You divide the whole thing by 2 meters, and I get TB is equal to. So hopefully that helps you on that MyLab mastering. I got 5 times 10 to the 4 newtons.
There's a question on the ed.
Yes,
the question asks, will tipping over questions not be on the exam, like the one we skipped about the max angle in the refrigerator, or a candle tipping question like in the Chapter 8 homework? And I think by exam, they mean the midterm tomorrow, not the final.
Okay, yeah, the test, yeah.
Yeah.
So let's distinguish those, because that is important. On tomorrow's test, there will be no tip equilibrium, like stability questions. Let's call it a stability question, since I skipped that. There'll be static equilibrium questions like this one, though, for sure. Does that make sense?
Okay,
But
thank
no,
you.
like, base of support stability. Let's just sum up more hints. Once again, there's a couple of conceptual multiple choice questions. You know, it's keep an eye on the time. I think it's really good to bring an actual watch, one of those old analog watches that isn't one that communicates with the world. The other thing I want to say is that I do have Kai Yunshu, I think, listed as Ed Reader. So for next time, Ed Reader. Wednesday is Kai Yunshu. But thanks so much today to Raphael. Really appreciate it.